Hi, good afternoon everyone. I'm going to get started straight away. I'm going to try and pack a lot into 60 minutes, which is always my problem. My name's Steve. I'm a Microsoft MVP, Pluralsight author and engineer at Elastic. Before I get into how you can contact me, there's a bit.ly link on this slide. If you grab that, that is a link to the slide. So if you want anything to review afterwards, or all the resource links and things, just grab that one link and you have everything you need. So if you do want to reach out to me, I'm at Steve J. Gordon on Twitter, same username over on Mastodon, just in case. And stevejgordon.co.uk is where I blog pretty infrequently at the moment, but hopefully more so in the future. So I'm going to talk to you today about writing code with code, and specifically using something called the Roslyn APIs. So to set expectations, we'll do an intro to Roslyn, so don't worry if you've never heard of it or you've never sort of worked with it before. We'll talk about what it is and why you might use it. We'll specifically then look at some demos around visualizing syntax trees and generating code from those syntax trees. Don't worry if you don't know what a syntax tree is, we touch on that too. And specifically where this is kind of applied practically is in code generating the next version of the Elasticsearch .NET client. So I'm going to talk a little bit about like how we determined creating a spec, transforming that spec into sort of models that we can sort of represent with C# types, and then actually building those syntax trees, emitting the C# files, and some of the lessons learned and things I would probably do differently with the knowledge that I've learned as I've gone along. So let's start with Roslyn. Roslyn was originally the code name for a project that kicked off what we're about to talk about. Microsoft are pretty good at good code names. Often they then ditch them at release and come up with a boring, bland product name. They kind of have. The .NET Compiler Platform SDK is kind of the other name for this thing. But Roslyn, fortunately, is stuck. So you will still find stuff in the documentation and the repos, and you can search Roslyn C# and you'll find probably what you're looking for. So as I say, it was sort of initially kicked off in 2010, and then I think it was sort of first released after some previews in 2015. And ultimately what Roslyn is a set of open source compilers for C# and VB.NET. Open source is pretty self-evident. It's on GitHub. You can view the code, you can play with the code, you can learn from the code and create issues, all of that kind of stuff. Compilers for C# and VB.NET. So the interesting thing there is that the compiler for C# is now written in C#. So to compile the compiler, you use the compiler that you've just written. And same for VB.NET. So the interesting part of this particular statement is open box. Traditionally, compilers have been quite a closed box. You put source code in one end, and out the other you get some kind of artifact, like an executable or a DLL. And what happens inside is kind of opaque to you, and you can't really access any of that information. And you might not think that's important, but the Microsoft team did, and ultimately what they've set out to achieve is producing a compiler platform, which is basically opening the box and giving us access to the APIs that Roslyn can give us to see what the data structures are that the compiler can see and hook into various points along that compiler pipeline if we want to. So this is used heavily inside like Visual Studio to provide all of the features you're probably using day to day without really paying much attention to them. Ultimately, I summarize this as the maker of squiggles and the finder of things. It's what understands your source code and is able to give you hints and IntelliSense, but also to highlight when you've made mistakes. If you forget a semicolon on a statement, it can give you a syntax error squiggle that tells you you've done that. And also we have other sort of more advanced squiggles that give us like code refactoring, so ways to maybe make code more concise or move to more modern C# language features. Finder of things like go to all, find all references, go to definition, searching for particular symbols within your source code. They're all enabled through things like the Roslyn APIs. So one of the concrete examples of where these can be useful is like building analyzers and code fixers. So a lot of these are already available to you, like just when you use the framework, but you can also bring in analyzers and code fixes in NuGet packages, so people can write these and ship them on NuGet for you. You can write your own internally within your business. So ultimately what an analyzer is it's something that contains code that recognizes some violation of a rule. And that rule can be pretty much anything related to the code that's been written. The structure of it, but style and naming conventions. You could, if you want to, write an analyzer that says you can never have a class name that has the word builder in it, and then enforce that across your organization. Now, once you've got sort of an analyzer to detect a problem which will appear as a squiggle in your code base, and you will configure that as maybe informational or warning or error, it's nice if you could also have something that fixes it for you. Rather than just telling you you've done something wrong, here's how you actually change your code to apply with the rule. And so a code fix is essentially that. It's something that's actually going to fix that violation in the code for you. Because we have all of the information through Roslyn about what the syntax and semantic meaning is of the code. I'll show a quick demo of sort of analyzers in action once the resolution fixes itself. So inside, this is actually something we're using inside the Elasticsearch code base for the client. And so as a library, we're recommended that we should apply configure await false to the end of anything asynchronous. Don't worry about why specifically. I don't have time to go into that. But we're doing it, and we can easily forget to do this. So if I actually delete this here and just give Visual Studio a second or two to realize I've done that, we get a squiggle. And if I hover over this, we can see it's telling me I'm possibly missing a configure await false here. So we've installed through a NuGet package an analyzer called configure await checker, and then this picks up the fact that we haven't applied the configure await on the end of this method call. And so if I go in here and I can say, well, I want to correct that then to put it back on again, and that's the code fix, putting that back for me. Similarly, in Box, we get something like if we forget to await an asynchronous method, again, Visual Studio will moan at me here and say, because this call is not awaited, execution of the current method continues before the call is completed, and then says to consider applying the await operator. And again, we have a code fix to add that back. So that's kind of, in a nutshell, some of the uses that you probably use daily inside Roslyn. Something more exciting, more recent, is source generators. This isn't a full talk on source generators. There was one this morning on incremental source generators. But just to summarize it, if you haven't heard much about these are a C# compiler feature that lets developers inspect user code while it's being compiled. You might think, well, do I care about that? Why would I want to know about that? Well, you can develop components that run during that compilation of your code to access the rich metadata about the code, the syntactical structure of the code and some of the semantic meaning. Again, you may still be thinking, okay, I don't care. You can create new C# source files at this point, so you can create them on the fly and add them to the compilation. And if you're still searching for reasons for it, let me give you a couple of examples. So where these are typically useful is reducing boilerplate code in applications. So an example in the Microsoft Docs, I think they actually now ship the source generators to fix this, or to help with this, is when you need to do like inodeprive property changed, and you need to implement that, and there's lots of boilerplate code you'd have to write. Today, you can just plug in a source generator by putting an attribute on a few things, and then the source generator at compile time can put all that boilerplate into your compilation for you. And that saves you a lot of code that you would normally have to write by hand and avoid you making mistakes and missing things. Another more interesting example, I think, is where we can actually improve the execution time of code potentially. So inside system text JSON, when you're serializing a type to or from JSON, the first time that happens, typically a serializer is going to have to start doing some inspection, usually using something like reflection, to understand, okay, well, this is the class they want to serialize to or from, here's the properties it has, here's the attributes, some of them have JSON ignore, some of them don't, here's the JSON property name, etc. So it needs to build up that model and that meta information to perform serialization. And that happens normally at runtime, and it gets cached, but it's still overhead. With source generators, we can actually do that up front, because we have the finished code that you want to produce and you're compiling. And so the source generator can see the same information about what properties are on the types and what attributes are applied. And so it can spit out a C# file for you that contains all of that information pre-calculated and optimize source code serialization. So that's pretty cool. We're not going to spend time on compiler theory, but just very, very briefly. There is a compiler pipeline. So ultimately, we write C# source files. They go into the compiler. It has to parse them. It has to understand where the tokens are in that text file that we've given it. We have to identify any symbols that have been declared in our source code, so methods and classes that we've defined. Also, methods and classes that have been defined in stuff that we're importing. So, NuGet packages we've pulled in. And then there's a binding phase to understand, so what are the results of expressions and variables in our code? What do they actually bind to, and what symbol do they bind to? And then finally, emitting IL. And so this is the phase where we actually produce IL code that actually is the result of the compilation. So C#, VB.NET, F# compiled to IL. IL is an intermediate language. So C#, VB, F#, high-level languages, machine code, low-level language. The intermediate language sits in the middle. And the nice thing is the compilers all just have to know how to produce IL code. and that can run on any architecture, on any platform where .NET can run. And then the runtime is responsible for taking that IL and just-in-time compiling to machine code. So as methods are needing to be invoked, if they haven't previously been compiled, then they can be compiled at that point. Roslyn includes a very rich compiler API that maps very nicely to that compiler pipeline. So you can see there the parsing phase has a corresponding set of APIs within the compiler API that to do with managing syntax trees. There's an API for symbols, there's an API for emitting IL code. And so it's these APIs that we're going to be sort of talking about. Specifically, we're going to focus in on this level, the parsing level and the syntax tree level. So let's introduce syntax trees. Syntax trees are the result, basically, of the analysis phase of the compiler. So as that parsing phase has gone through the code and it's worked out where all the tokens are, it understands the syntax that we've written. And so from there, we can build up a tree representation of that syntactic structure of the code. And this includes three main things. Nodes, which are generally going to correspond to kind of language constructs. So like a class declaration or a method declaration would be defined as a node in this tree. Nodes will always have a parent except for the root node, and nodes may have child nodes below them. So a class can have methods and properties, and those are nodes below it. Nodes also are made up of tokens, and tokens are really the individual language keywords that correspond to that declaration, to that node. So for example, we can put a public keyword on a declaration for a class, and then we've made it public. But that token has to be attached to that node so that we understand that it's part of that declaration. Tokens are kind of terminators within the tree, although they do have trivia attached to them. And trivia is anything within that source code file that isn't something that's going to be involved in the actual final compilation of IL code. So this is white space, new lines, and also things like comments, single line comments, multi-line comments, XML documentation comments. That's all structural things that we can include in a C# source file that aren't necessary for compilation, but we do want to represent them in the tree so that we understand where those things belong. Because, for example, with an analyzer or maybe even a code refactoring, if it's going to move some code around in that tree, it needs to make sure that any comments that belong to that line follow it around as well. Ultimately, what a syntax tree gives us is the ability to interact with source code in a more meaningful way. So we're no longer just looking at a text file that needs parsing, but we actually have a data structure now that represents everything that we've defined for our program in that source file. Very important points about syntax trees. So they're immutable, as are the nodes and everything below. So this is important if you're making changes to a syntax tree. You're not changing anything. What you're doing is saying, I want a copy of this node with these changes applied. Now, internally, this is all done as sort of in a relatively highly optimized way to avoid sort of too much memory allocations, things like that. But ultimately, it's important because multiple different things might be looking at that syntax tree at the same time. And we don't really want to have locking. We want these things to be thread safe. So if you're going to change something, you get a copy of that thing with the changes applied. The other important point is that they're round-trippable. So you can parse a C# source file through the compiler and you'll get a syntax tree. And because that includes everything that's in that file, including all of the detail about the trivia, you can return back to a C# file or just a text file ultimately that has the exact same representation of that source code in it. So entirely round-trippable. So there is some tooling that we can use to kind of get an understanding of what a syntax tree kind of looks like. This isn't installed by default, but if you want to, this is where you need to know the product name. On the right there, you can see the .NET Compiler Platform SDK is the component I've installed. You can find that under Visual Studio Extension Development if you want to install that piece. So with that, let's have a look at a syntax tree. I don't want that one. So in this solution, and I've got to give a link to this at the end, but it's not very exciting. We have a single program class in this single project here. So it has a program main method, has a very simple data class, and we just basically create an instance of the data class and then write something out. The code is not exciting, nor is it important, but what we'd like to do is actually understand what the syntax tree looks like. So if I go with that tooling installed, if I go here to other windows, I can bring up the syntax visualizer. Let's pin that over there. Hopefully this will be big enough. If it isn't, there's space to come forward. So if I click in this code file somewhere, it populates the syntax tree. So you can see the root of the tree here is this compilation unit, which is basically just a C# source file. And if I click on this, you can see it highlights all the text that belongs to that node and below. So if I click here, I can see I've got a file scope namespace declaration. So using the file scope namespace syntax here. So although this isn't curly braced and then indented like a traditional old style namespace declaration, file scope namespace is still applied to the entire file. So everything in this file belongs to that namespace just by the nature of how this feature is defined. So everything appears under it in the tree by being indented. That is defined with a keyword. So this is a token, which is a language keyword that we have in C# in the grammar. And then you can see here the trailing white space. So we can identify where that trivia is appearing to. We then have an identifier name, which is made up of an identifier token. So this isn't a language keyword. It's something we decided to name the namespace. And then we can see we even have the punctuation represented as a token, the semicolon here, and then that's followed by a new line. We have two class declarations. If I expand this first one and we dive down a little bit into the method, and we go down to the block. So this is the method body. You can see again, wrapped in open brace, close brace tokens, we have our two statements. And the local declaration statement defines the variable, and then we have our expression. And if I dive down here and click on the semicolon token, at the end of that, we have multiple bits of trivia applied because we have white space, then we have our single line comment on that same line, and then the end of line trivia. So this is all the trivia that's attached to that token so that we know what's actually in this file. So that's one way you can kind of get started with getting a view of the syntax tree. Another thing I've installed is something called the DGML editor, which you can find if you search other components. And if I right-click on this class declaration, desperately try and fit this on the screen, let's do 125%. We get basically a kind of graph view of that syntax tree. So I've chosen to start at the class declaration, and you can see below that we have one of its children is the method declaration. One of that has a child of a block node, and then we see, don't want to move stuff around. We see the statements, statement there. So obviously you can see there's lots of syntactical information that has been identified here. We have all the tokens in green. We have the trivia, so leading trivia that comes before a token is in white, trailing is in gray. And that can be kind of useful if you want to kind of get a feel for what a syntax tree looks like. I'm going to close that so I get some more memory back. Cool. So with that knowledge sort of set, let's talk a little bit more about how we're going about co-generating a language client. So Elasticsearch has grown over the years, and Elasticsearch is entirely managed through its HTTP API. So as features get introduced, the team add more and more endpoints. There's well over 400 endpoints there today, and for representing all of the data that can flow in and out of those, there's over 2,000 data structures used. There's requests and responses for most of those endpoints. Most of those have tens of properties. Then there's sub-objects below those that have to be represented. We have concepts like different queries and aggregations and filters you can apply. So it's a complex API. And our job on the clients team is to build the language clients that allow you to interact with that programmatically through various different languages. So with the version 7 language client for .NET, one of the major problems we had was that it's nearly entirely handwritten. And if you can imagine keeping up with a server team of hundreds of people who are producing new endpoints, new features, or modifying existing requests and adding new properties, that's a lot of maintenance work because the clients team is less than 10. And so ultimately, we're going to not be consistent with the API. You know, in the original days, it was easy to kind of hand roll this stuff and keep up at a reasonable pace. But you know, we have to, when someone tells us they've added a new endpoint, we have to see if they've written documentation yet. And if they have, we can see the docs and we can get a view for what's available there. If not, we have to go to the Elasticsearch server code base, which is Java. And we have to basically reverse engineer all of their modeling there to figure out, okay, well, we want these properties on the C# model then. And so, you know, we're getting out of consistency. We're never going to release things quite at the same cadence that the server team can. And that's a problem. And so for version 8, we started thinking about how we could get more intelligent about this. You know, it was the time to make the move to optimize this. So for .NET and Java in particular, we kind of basically decided that we'd create the next generation of those clients. And specifically to make things easier, we would look to try and code generate a vast majority of them based on a formal spec. So ignoring the spec for a second, we'll come to that. If you're told you need to generate some C# files, what are the first possible options you might think about? Well, strings and string builder is a valid way of doing code generation. You can have strings that represent, a structure of a C# file that you want to produce with placeholders that you populate for each type, or you could break them down into, a representation of a class and a method, and then chain these things together with string builders. That's a valid way of defining ultimately a text file, but it's a bit brittle. You don't get any kind of checking that you're doing the right thing. If you misspell namespace, you will maybe only find out about it when you generate your client, and then you try and compile the client, you find the error, and then you have to find the string that code was defined in. Another option that's maybe a step up, but still really working with text ultimately, is templates. So something like T4 or Razor. We were actually using the Razor engine in the V7 client for the small amount of code gen we did do. We basically created Razor views that represented the structure we wanted to generate, and that can include constructs like loops and things. And then you have the view model, which is something that you can populate for each type, and then use the Razor engine and model binding to actually produce the final file. And that worked quite nicely, but it's still kind of templates which are text. Ultimately, what I landed on was I wanted to try and play with the Roslyn APIs, because my thought was, well, we can construct a syntax tree with the Roslyn APIs and generate C# from it. Because just as we can parse a C# source file, and we can get to the syntax tree, as you'll remember, it's entirely round-trippable, but we don't have to start with parsing a file. We can actually construct programmatically that syntax tree and then just emit the file from it. And so let's look at what that looks like in .NET. So I do have another project actually in this solution, and that has a file in here called spec.json. This is like a really super simplified version of the Elasticsearch spec. It doesn't define enough to be a rich specification for defining classes, but it's enough for getting started. So you could generate any spec you want. You can have any format you want. As long as it contains the information you need to understand what classes and things you want to produce, you could create one. But we've chosen a basic JSON structure. So we have an array of types. The type has a type name, and it might have an array of properties, and the property is just going to have a type and a name. So a very simple spec, and we have two classes defined. Inside this project, I have a reference to the package microsoft.codeanalysis.c#, which gives me the compiler APIs and some specifically stuff for working with the C# syntax tree that we're going to need. So this is where the Roslyn APIs come in. And they've obviously used a different name to everywhere else that we've just talked about, but as long as you know where to find it, you know what you're looking for. The program for this is only 55 lines, I think. Most of that is actually parsing the file and using statements. So the first part of this program is basically, look, I want to deserialize from that JSON spec file that we've got into some types in .NET that represent it. So I've got a schema which has a collection of schema type. The schema type has the type name and a collection of schema property, and then we have a type and a name, and those are strings in this model. So that allows us to get some objects from in C# that represent our structure that we want to generate. And then we're going to create this class declaration syntax array. So this is basically one of those syntax nodes, or a set of syntax nodes relating to classes. And so we do that by accessing all the types on the schema. We're going to just do a link select, and we're going to use this helper class create class down here to actually create the class declaration syntax. So that takes in the class name and any properties that are assigned on that spec. So then what we're doing is actually creating a class declaration. And rather than newing up the class declaration syntax object itself, we're using this method on the SyntaxFactory. And the SyntaxFactory is, I've got a using static here because otherwise your code gets littered with SyntaxFactory dot all over the place, and that gets hard to read. So I'm just going to call the factory method here to create a class declaration. And it enforces the fact I have to provide a token as the identifier. So this is already giving us some level of sanity checking that we're generating something vaguely valid as a syntax tree. If we were just doing text, technically you could miss the identifier, you probably wouldn't. But here we're getting it enforced by the syntax tree understanding there's definitely going to be an identifier on a class, please give it to me. And that's just the class name that we passed in. And then, by default, we're not going to have any modifiers, any keywords applied to that declaration. So we want to add a modifier here And the modifier is just, we're going to attach a token of syntax kind public keyword, so a language keyword. So this syntax kind here contains basically an enumeration of all the keywords we might need from the language. So we now have a class declaration, and then for every property, we're going to add that property as a member, so as a node below that class declaration. And add members, in this case, we're creating properties. Now, the important point is this reassignment to the variable. So if I take that off for a second, that looks valid, probably. I can't seem to scroll up for some reason. That looks valid, but the problem is what we're doing here, because this is an immutable structure, is we're not actually updating what this variable is referencing. We're calling add members, and that's returning to us a class declaration syntax, which is the new copy, the modified version, with the changes we want. So we have to make sure we reassign that back to our variable. Otherwise, when we spit this thing out, we won't have any properties. To declare a property, we need the identifier name for the type and the identifier for the actual property. Again, we're going to make it public. And then we're going to need some accessors so we can get and set the value of this property. So in this case, I'm using this add accessor list accessors method. Bit of a mouthful. And I like this one because it takes a params attribute. So I can just pass in two accessor declarations, comma separated here, and it will just take those in for me. So we're having a get and a set. And we have to put in the grammar and the punctuation, so the semicolon token here of syntax kind, semicolon token. There are other methods that you've got, so there's various with methods, so you can create like with accessor list, but this requires an accessor list syntax, which you create through the factory, and then you have to pass it a list. So it's a bit more verbose, so I prefer the kind of add methods for kind of terser code. And that's it for declaring the class declaration. We're ultimately going to want these in a namespace, so I'm now going to use another factory method to create a file scope namespace declaration. Again, I need the identifier for that. And then to that, as children, I can add the class declarations. And now I've defined my syntax tree. So I'd like to spit this out. So I'm going to create a stream to a file, and I'm just going to call write. You can call write to on any of the syntax nodes, and it will spit out what's below it. So if I run this code, which is done, and we go to the generated code, not quite what we wanted. So we're missing spaces and new lines here. We have got what we asked for. We have a public class first class, but this is not something the compiler is going to be able to read in and compile once we actually try and compile it later on. So why do we have that problem? Well, we didn't actually specify any trivia. This code just specifies the nodes and just specifies the tokens we want. Now, it's possible to add trivia, like we can do with leading trivia, with trailing trivia, and then we can attach the trivia that we want. That would get quite painful quite quickly. And ultimately, I don't care too much about the formatting, so I'm just going to cheat, and I'm going to call this normalized whitespace method. And so what this does is just apply standard whitespace rules for where new lines should appear after semicolons and braces, and you're going to have a space after a keyword before the identifier, that kind of thing. And so then if we rerun the code, we now get what we're hoping for. So we now get our generated C# file. It's something a C# compiler can actually compile. Now, personally, I'd love an extra line there because I just like that. But that's not the rules. So that's what's generated. Try not to get too precious over your generated code files. Most of the time, you're not modifying these things by hand. You might debug through them occasionally. You might check them when you start code generating to make sure they're giving you what you're expecting. But the formatting is not important. There are ways to pass like formatters in. You can even, I think, pass in your editor config rules, and it can apply those in the formatter. That stuff we're not worried about. But ultimately, we've generated the file. So actually, one other thing, you might be wondering, how do you know what the Roslyn API calls are to generate your C# code? And often you don't. So I start with this really handy website, which is basically where I've lived for like a year. roslynquoted.azurewebsites.net, nice open source project. And if I paste in some C# code up here, and I click get the Roslyn API calls, the output here is close to what we wrote by hand. You can see by default, this project just tends to use the with method. So you can see with accessor list, then we create an accessor list, then we give it a list, which has got an array to populate the list, which is weird. But ultimately, it's giving us an example of all the nodes we need in the structure we need them, and the tokens that we're applying to those, the modifiers. And so you can kind of take this and then slim it down if you care to slightly terser code. You can even click to preserve original white space. And now if I generate this, you get all of the tokens have leading and trailing trivia, sometimes empty. And up here, we can see we've got a space after the namespace keyword. And you can see that that's obviously much longer, and that's why I don't bother messing around with that stuff myself, because I don't care that much about the formatting of my generated files. So moving on then, let's think about generating the .NET client. So we're going to need a spec. And so how do you define a specification for something that's quite complex, like Elasticsearch? So I wasn't there when the team started this sort of piece of work. So this started, I've been at Elastic nearly just over 2 years actually. And this kind of kicked off just before I joined. And the team first assessed something like OpenAPI. This is a specification for defining HTTP APIs and specifying them. Ultimately, at the time at least, OpenAPI was a bit too limited. Elasticsearch is very complex, and we'd need custom extensions added in there to handle some of the edge case things that we have and the weird polymorphism that some of the request and response types have. Ultimately, our problem's about representing data structures. Endpoints are quite easy to represent and specify and document. The data structures are harder. As I say, Elasticsearch APIs, sometimes they have unions of the types they might return, so a property might come back as a Boolean in some scenarios, but sometimes as an integer. We need to know that so that the C# code can be built to try and handle that problem. Similarly, you can send any number of queries when you're doing a search, and all of those have different structures that we need to represent those, but ultimately the server will handle whatever data it gets. But we need to model that somehow. The other thing is managing an OpenAPI spec for 400 endpoints and over 2,000 data structures by hand in YAML or JSON is not going to be that fun. The output today is about 180,000 lines, so managing that sort of size of specification by hand is probably not a great idea. So what the team decided to do is actually let's deal with the data structure issue and model our data structures using TypeScript, because it's a static type checking is in there, so we can actually kind of make sure that our types make some kind of sense. It's a type system built to represent JSON and JavaScript. We have strong IDE support for working with it. Across all the developers, no one was sort of against using it in different languages. And it has its own compiler APIs that you can hook into with libraries like tsmorph to do some clever stuff that we'll talk about later. So this is ultimately an example of kind of what we've ended up with in terms of defining our types. So here we're defining a request. This isn't the complete request. And you can see we have inheritance. So we can say, well, look, there's a bunch of stuff that's an all request. We'll put that in a base class, and we can say that this extends that. The fact it's just called request, it's actually a search request. There's namespacing that we're using to figure out where these requests belong to. But we also have meta information that are basically specific tags in the comments. So in this case, the spec name, when that was introduced in the server API, is it a stable endpoint? And then we have to define basically 3 main things about the request. The things that could appear in the URL path, the things that can appear on the query string, and the things that might appear in the body. And we have separate objects to represent these. So here for the path, we have an optional index that can be passed in. So when you do a search, you can either search everything and just going _search, or you can provide the index name or a set of indices that you want to search against and limit your search results. And so that's optional on the path. And so we define that with an optional property here with the question mark. And then we define a type for that. So this is indices, which is actually a union of index name or index name array. The reason we have to be very specific, though, you might think, oh, we could just use the array, can't we? But the problem is, on some of the responses, we might get back either a string or an array containing strings to represent the result of some index on that response body. And so we define it very explicitly to say what exact data types we might expect in all scenarios. And then we also have, like, index name here is basically an alias over a string that gives us kind of a strong name for that string type that's used across our code in our TypeScript model. But ultimately, it's just representing a string. On the body, some of the things that are interesting here. So we have a property defined on the body for aggregations. Don't worry about the typing of that for now, but the interesting thing is that we have this alias. So when you actually send a search request to Elasticsearch, you can send it aggregations optionally, and you can use aggregations as the property name in the JSON. You can also call it aggs, and the server will deal with that. On the way out, that's not a problem for us because we can choose which we use. But if the server returns us a query in any of the data structures, it might choose one or the other of those names. And so we have to, again, in the C# code base, we have to have a custom serializer that says, okay, I'm looking for either ags or aggregations, and that binds to this property ultimately. So we have to declare that information in the spec. We also put like documentation information into the spec here, and then that can be picked up by the language clients to include their own documentation where it's relevant. A response is interesting because we have user-provided types. A response is going to contain generally search results, which will include the documents that you've matched. And those documents are the things that the user indexed. So we don't know what the structure of those is. We know what our our response body is going to have in terms of fixed properties, but we need the generic system in TypeScript to represent there might be this other sort of user-provided thing. And so ultimately, the hits on the response body here is this type hits metadata of t. Another interesting thing in here is total, is pain, because again, depending on how you've configured your request, you might get back an object that contains some properties, the total hits object, or you might get back a long. So this is yet another case where we need to know that as a language client to be able to deserialize either option, depending on what we're given. And there's no way of knowing up front in all cases, because some of these things are controlled by server-side configs as well. Hits here, hit of t, you can see there where this applies is in the source. So if you get a hit, a result back, we have some fixed information the server's always going to include, and then if you've asked for it, the source, which will be this t document. And we can convert that in C# quite nicely to generics as well. And then when you do a search request, as a generic argument, you tell us what the type is you're expecting for your results, and then you just, we can deserialize that for you using our source serializer. This is another interesting concept we had to come up with, was how to model those polymorphic scenarios where something can be sent in multiple forms or maybe received back. For queries, what we've done is model this as a kind of container. And basically, the container lists all of the possible strongly typed queries that Elasticsearch supports. And then we mark that with this attribute here that says this is a container, and it's going to contain all the variants that we could possibly send up. And then the language clients are free to do with this information what they will. They have to come up with a language structure that makes sense in the language to represent that and how you work with it. Ultimately, in C#, we still end up with this container object, and it takes one of these queries that it's going to contain, and we just constrain them by a base class to say all of these things are valid inside that container. Now, the other important thing we've got to do is validate this spec. We've generated this massive TypeScript specification, and we've modeled it, and we've got all the strong typing in there to make sure all of that logically makes sense as a model. But how do we make sure it works with Elasticsearch? And so for that, we hooked into the integration tests. So ultimately, we have this thing called a flight recorder that we run, and we run the integration tests, and then we just capture all the request and response JSON for every test to every endpoint. And then ultimately, what we can do is just check that those serialize and deserialize to and from our TypeScript types. So if we get a response that has a property on it that we haven't defined in our model, then we get an alert and we can go and fix it. And so we get a lot of tests for free, and we don't have to think too hard about the problem because the Elasticsearch team will create the integration tests as they add features. And this runs as part of PRs. So if you do a PR to the specification repo, here Seth's modified the user profile, and it detects all of the endpoints where that might be used somewhere in the request and response below. And so you can see, for example, security to authenticate has 15 recorded requests and responses for different test scenarios that will give us different examples of valid request and response bodies. And so it's checked that that type is still can serialize to and from those. Then we need to generate the spec. We've got the TypeScript model, but how do we create the spec? Now, in theory, we could generate the C# code from the TypeScript by using the TypeScript APIs to access their abstract syntax tree and then generate our code. Ultimately, that's quite low level, and the main problem is it's not fully constrained. Different language clients and different authors of those generators might infer different things from the syntax tree in a different way, and that's not ideal if you're trying to generate consistent clients. So we decided what we would do is transform that TypeScript to a simpler specification, tailor-made for our needs and unambiguous. So this is kind of our code-gen pipeline. We have all the TypeScript files in our sort of project for the TypeScript, and then we have this thing called the spec compiler. So traditionally, TypeScript would compile to JavaScript. What we do is we hook in through that tsmorph library that I touched on earlier, and we access the syntax tree, and then we basically inspect that and go, okay, well, this is the JSON structure we want to produce for our schema. And so that's ultimately what the output is for our spec compiler. It's our single schema.json file that lists all of the possible endpoints and then also all of those data structures and the annotations that go with them. So from there, we can create our code generators. So I've created a .NET code generator that spits out most of the .NET client. The other language clients are doing the same for theirs. The dynamic people have got a great time because they don't have to worry about the typing so much. The Java, Go, and C# people, we're having to think a bit harder about how we model these structures and some of these concepts in our languages. Now, I have some history with the previous clients, and I've tried to apply that most of the time, but we've also had the opportunity to rethink some of these things and how we model them. And also, we've had to make decisions around standardization in terms of the code generator is going to have to do this thing once for this concept, so making sure it applies and works in all cases. The other interesting thing we could do, and we're starting to play around with, is we have now an open API generator that takes our schema.json format and spits out an open API spec. And then teams within Elasticsearch that want to work with open API can build like API documentation off of that spec. The exciting idea is that we could even generate some of the server-side code, because if we get entirely schema-driven and we agree up front what the specification for endpoints is going to look like and how we're going to type them in our TypeScript model, we build the schema.json, and that's our single source of truth for what Elasticsearch's API should look like. So we generate the clients, but we can also generate the endpoints on the server and their models. And that would get us to a really nice place where, consistency-wise, we should always be consistent. And if we're wrong everywhere at least. Quick demo of schema.json. We won't, as I say, it's like 180,000 lines of code. We probably don't have time to look at all of it. I've grabbed two examples. So if we go to line 9,840 of the schema, we'll see the definition for our search endpoint. So this is that same endpoint that we've been talking about so far. So you can see the name here. We get all that meta information. So if we've attached the documentation URL, the description, we have the types for the request and response. So you can see all of the types come out into the spec with an actual namespace, so we don't have any clashes. So this is why we don't name this thing search request in the spec in our model. We can see, does it require a body? No. It takes application JSON, it returns application JSON. It's been there since the day one, it's stable, and it has two URL paths that could potentially match for it. Because we have that optional index on our specification, if you don't provide that when you build up your request, then obviously you're searching everything here with that URL, but otherwise we need to apply it. So the language clients have to know all the URLs, and they have to know if properties are set on there, however they've modeled a request, if the properties are set for that define the indices that you want to search against, we have to use this other URL. So that's that part of the spec. If we jump down even deeper, we'll get to the search request. And again, this itself is quite big, so we won't look at the whole thing. But ultimately, the object starts about here, and the top part of this defines its body properties. So to align with what we saw in the example code earlier on, there's that aggregations property that is available. We have a list of any potential aliases that the clients can then decide how they handle aliasing if they need to. This property isn't required on a search. And then we have the type information. So in this case, this type is a dictionary of, and the key for this is an instance of string, and the result, the value, is an instance of that aggregation container. So we looked at query container, aggregation container, very similar concepts. We have many possible aggregation types that you can send in, and the container basically is a way of constraining that to all of the possible built-in types that we could represent an aggregation with. And that ultimately is what that entire file contains, just for all of those 400 endpoints and types that we have. Eventually. So in terms of .NET code generation, our first job is deserialize JSON, pretty easy. Then I do a phase where I'm essentially doing what I call building the context. So the JSON file contains everything we should need to know about the Elasticsearch API and its types. But it doesn't have enough information for me just to generate blindly. I have to do some sort of modifications and understanding of what that means to see what's valid for C#. And we'll talk specifically about what I call the mark and enrich phase, because it sounds fun. And I'll talk through what that actually does that is sort of applying stuff to those contexts. But ultimately, once we've got all of these contexts for every type we're going to generate, we can do what we've just seen before, just on a slightly more complex level, and build up a syntax tree. using those Roslyn APIs. And we just build a syntax tree for each type that we're going to generate, and we emit a file or set of files potentially out to the project that we're generating into. So some of the things we have to think about. So one of the important things is naming and namespaces. It's possible the TypeScript model includes names for types that are not valid in C# because they conflict with a keyword or whatever else. There's often cases where some of those types have underscores and different casing potentially as well. And so we have to basically sanitize the naming of all the types. Sometimes we can do that on a rule-based basis. Sometimes we just have like configuration as code that says, rename this thing on this type to that, because it makes more sense. Also, we have to think about namespacing. We don't want a namespace that says underscore global in C#. I think it would be unhappy. We want it to be in our root project namespace for our assembly in that scenario. And then we do introduce namespacing in the C# library to avoid type name conflicts, but we've tried to limit the depth of that. So in the TypeScript model, the depth can get quite far down. I think you could have like 5 times for different parts of the namespace. We try and bring that to a more sane level of less namespaces. So if you're using the different parts of Elasticsearch APIs, you don't have to bring in lots of using declarations for them. We also walk the type hierarchy, so looking at the base types defined in the spec. The base types in the TypeScript model are there as a convenience for us not to have to retype all the properties on every request. They don't represent an actual construct on the server necessarily, because the server may model that differently. So what we've decided to do in most of the strongly typed languages is actually just flatten all the properties from all those base types onto the search request in this case, for example. So that request base class just contains some properties we hoist up logically inside our kind of context. We have to identify the relationships, so we resolve all those schema namespace names. We have to identify, okay, well, this property has this type, and that's this C# object over here that we've pulled from the specification and deserialized, and how they interrelate. So we can navigate those relationships in any direction. We mark all the request types. So anything that's used on the request, you're going to need to be able to modify it and set its properties, because consumers are configuring the request they want to send. Response types, we don't expect you to modify those, so we make them basically read-only, and we deserialize them and give them to you. We also mark all those special concepts, those containers, the variants. We also have something called internally tagged unions, which is another way of representing the polymorphic JSON we might get back. And ultimately, we also want to simplify some of those type aliases. So where we had like index name is an alias for string. That one we actually keep because we have some special logic around index name, but that's used a lot in the TypeScript model. And many of those, we don't want our users to have to basically, we'd have to create a type, a class or a struct that wraps a string in order to model that. And then you'd have to construct that through like a constructor or something, or we give you implicit operators. That's a pain to work with, and it's hard to reason about. So we just simplify those to whatever they alias to the string or the integer in the properties that we're generating to make working with the API a bit easier. And then we also mark some types that need special serialization. So the bulk API takes new line delimited JSON, not just a standard JSON structure. And so we have to know that that's going to need custom serialization logic that we're going to create. And so we basically stub that out, and then we can manually manage that code ourselves in the client. So what does our generator code look like? Pretty much what we saw in the demo earlier on, just slightly bigger amounts of code scattered throughout my generator. So when you see a request on our type, or the type in our schema, that's one type, but in C# we're going to generate probably at least 4 classes for that. We generate a class that represents all of the query string parameters. We call that the request parameter class, and that's for the code you're seeing here. We also generate the request class itself that models the body of a request. And then because we have another syntax for fluently defining requests in Elasticsearch, we generate what we call descriptors, which is how our fluent syntax is put together. And that we usually have a non-generic and a generic version for reasons for when you're working with those in different ways in the API. So here we're doing a class declaration for the request parameter class. From the context, we get the name, we add the modifiers, we can add a base type, and then ultimately we create properties for each of its query string parameters defined. And we add that add class there, just adds it to our root namespace declaration. We also then need to figure out what constructors we're going to need on the request. So we saw a request that had an optional path parameter. Sometimes requests have a required one. And if you have a required one, what we do is generate a constructor that enforces that so that consumers can only create the request with the required path parameters. So we do all of that sort of analysis up front. And then ultimately, we're generating, again, another class declaration for the request class. We add all of our various members, the constructors, some common properties, a property that maps to the generic argument, query string parameters, and then the body properties. And so body properties here is using essentially my own SyntaxFactory, which helps me create this serializable property syntax. So I take in a property here, which is basically what represents a property in my context. I do some type name resolution to find out what the fully qualified name of the type is. So rather than figuring out what using declarations each file is going to need, I generally just use the fully qualified name of the type where we're declaring properties and things like that. So once I have that information, I can create the property declaration. We can add any attributes that are needed for system text JSON. So the JSON include the JSON property name, and we get all of the property names off of the spec. If it's used in the request, we add a getter and a setter. Otherwise, we don't. And that's pretty much it for our code generator. So let's now think about what I've learned through this process and what I would do differently. So we have a working code generator that's generating not all of the endpoints yet, mostly for the fact that we haven't spent the time testing. Everything looks good. But we have a working generator, but it was put together rather rapidly through evolving knowledge because we were defining the spec as we went. We were fixing problems. We were coming up with other constructs in the model for Elasticsearch's data structures that we needed to somehow specify. And so we often found ourselves kind of having to adjust based on new things we were adding to the spec, or even new kind of things like those variants. And so as I've gone, it's got a bit spaghetti code. We all try and write clean code, but this is a bit of a mess. So it needs refactoring. And also, I've understood where the various things are that you need to customize in this. Because ultimately, what I'd like to do is productize this so that we can get maybe an OpenAPI spec or another schema.json file for a different product, and then spit out a working client. But right now, it has a little too much knowledge built into the code about Elasticsearch and some special edge cases. So what I'd like to do is add like a pluggable transform pipeline to this thing that basically takes a set of defined JSON files that could represent how we would take the spec and then transform it. So this would be things like renaming those properties that conflict. We'd have a rename transform that you'd read in, and it would tell us what to rename. And so at this level, we're really just tweaking the spec that we've just read from JSON. It could include things like skipping certain properties or adding other properties. And so I'm thinking you probably have an I transformer, and then you plug those in through DI, and most of them will read in JSON input. Similarly, for working out what we're actually going to generate right now, it's just kind of an allow and deny list in code that kind of says, yeah, these are the endpoints I want to print out. We can make that more intelligent with a similar concept, some kind of filter pipeline. So we could say, well, have a filter that says we only want to generate endpoints that have been available or since this version or before this version. We only want to generate stable endpoints, or we want to generate this specific allow list of endpoints. Ultimately, I want to make this thing something that we can kind of hand off to other teams that makes it easier for non-developers in those teams to configure it through JSON files rather than having to kind of figure out what's going on. I want to kind of hide all the complexity of Roslyn for them. And the really cool thing that I haven't yet had a chance to play around with that I think would be really good and useful is to actually look at getting more intelligent with this. So part of the reason I chose the Roslyn APIs is there's a lot more you can do with it, including working with something called the workspace APIs. So the workspace APIs basically give us a way to hook into like solutions and projects. So there's an MS Build workspace that you can load up, and you pass it a solution location, and then you can access the solution, and then you can navigate through to see, okay, that solution has these projects, and it has these source files or these documents, and then you find all of the C# documents, and then you could basically build up the syntax tree and the semantic analysis for everything that's in there, essentially within that compilation. And then we can take the knowledge about what we're about to generate and kind of diff it, basically. So today, what the code generator does is it obliterates the generated folder in the project, and it rewrites every file for every part of the spec that it's generating, which is pretty low tech. But what we could do is say, well, okay, I'm about to generate this type. I know I'm going to have these properties. Can you find this type? Is that a symbol that's already in this project? Okay, it is, but it's missing these properties, so we're going to be just adding those. And that's where we could basically modify the syntax tree, so create a new copy of the syntax tree from that node with the changes applied, reapply that into the workspace, and then have it emit out the changes to C# files. So we're not obliterating everything every time. Because right now I have to basically git diff on the Elasticsearch client after I've run the generator and go, okay, it's added this stuff. The important thing is we'd want to detect breaking changes. If someone removes a property from the spec, what do we want to do in C#? Do we want to remove the property and introduce a breaking change? Or do we want to maybe preserve it and decide that we put a sort of deprecated, obsolete attribute on it or something? The other thing we could potentially do once we have access to this level of the code, because we understand the full project, we could actually then, in memory, compile the whole project. And we could check that what we've generated is actually compilable. Because right now, again, I run the code generator, I switch to my other Visual Studio instance that has the client, I do the git diff, check what's changed, and then I say compile it and say, okay, yeah, great, it's worked. You know, that's manual, it's not ideal. We could automate all of this through the workspace APIs potentially, and then we can just have basically a GitHub action that says, generate this version of the spec, please, and then give me a PR that introduces those changes. That's kind of where I want to get to with this thing. Resources, so I'm pretty much done. The link to the slides, again, writing code with code on the bit.ly there. So if you grab that, you get all the slides, you get all the links I'm about to show you. The demos that I've showed you are on my GitHub repo. They're not particularly exciting, but if you want to have a look at them, you can. This is the Microsoft page for the Roslyn stuff. So you can see here it's referred to as Roslyn, which I think is better. Roslyn Quota, definitely your friend if you're doing this kind of stuff, for just taking what you've already got, or you prototype what the C# is that you're going to generate, and then you go back to the Roslyn code, so get the Roslyn API calls you need, simplify them down a bit, and ultimately package that up as your code generator. If you want to look at the result of this kind of stuff, if you go to our Elasticsearch client repo and go to, there's a .generated folder in there, or underscore generated folder in there, you can find all of the generated files if you're curious what the ones we're generating look like so far. And our spec is public as well, so if you want to view that specification TypeScripts and if you want to contribute or just kind of see what we're doing in there, you can go and view that. And that includes all of our custom compiler stuff, I think, in there as well. The code generator for .NET is not public, I'm afraid, so you're just going to have to go on what I've shown you so far. Once it gets more refactored and productized for other teams internally, maybe we'll be able to release that as well and make that open. But right now it's kind of intrinsically tied to what we're doing, and it's a mess, so you're not going to see it. With that, thank you very much for coming. I hope this has been useful, maybe interesting, or just a good place to nap after lunch. Otherwise, find me online if you have any questions that pop up. I'm going to clear the way for the next speaker, but if you want to hang around for questions afterwards, yeah, come and find me. Thank you.